Hello everyone, my name is Blake Ocampo and I am one of the developers of the Molly Python toolkit. This is an essential toolkit for the creation of a lot of our cheminformatic workflows here at the Denmark group at UIUC, and we use it for the creation of large combinatorial libraries and allows us to manipulate a lot of these libraries in meaningful and reproducible fashions. Today I want to give you both a low-level and high-level overview of some of the utility that can be gained in our package and how you might be able to apply it in some of the workflows you might be interested in creating. Before we dive right into it, I want to give a quick aside about why we were even motivated to pursue this project in the first place, and a lot of it stemmed from our desire to create large combinatorial libraries of catalyst structures. Existing solutions often could really only maintain point chirality, and the more complex the catalyst, such as integrating features of axial or even planar chirality, often had problems with reproducing stereochemistry upon constructions of really large and complex in silico libraries, and that's where Molly really became an important part of our dream to have a convenient but even an extensible interface where we could unify all of these unique workflows that the Denmark lab had developed independently under one real umbrella. To begin, I want to introduce some of the key classes that exist within Molly, starting with the molecule object. Now, this is pretty simple. If you just import Molly, and if you're in Jupyter Notebook, you can actually visualize some of the molecules that you're working with. And you can take some file path to a mol2 or an XYZ file, load it in directly, and actually visualize this. And our representation you're seeing here is through our integration with Py3D mol. But if you're actually looking at the molecule itself, you'll see that it's made up of a few key components, including a list of atoms, a list of bonds, an array of 3D coordinates, as well as a dictionary of attributes that isn't defined at the moment, but you can essentially set them as you are going along if you find any properties of interest. The next key class is the atom class, and it's exactly as you'd imagine. If you have an existing molecule, you can run the method getAtom, and it can be an index, a label, or an element, and you'll return an atom with certain key attributes, including this element, isotope, labels, formal charge, as well as a dictionary of attributes that, again, you can define yourself. And the final key part of a molecule is the bond class, which operates exactly the same. You can get a bond that will be made up of different atoms, a label, and a bond type, as well as a dictionary of attributes. And what you might notice is that all of them maintain this dictionary of attributes, and this allows you to store any native Python property as an attribute of either the full molecule, the individual atoms, or bonds, which means if you envision running a script for something, if a certain atom has a certain property, you can assign it to that atom and make sure you don't have to cross-reference a separate list or etc. for a bond or a molecule itself. Another key class I want to introduce is the conformer ensemble, and you can load these in directly from a multi-mol2 file, and this is what you'll see through our Py3D mol representation. Now, this is made up of a collection of individual conformers, as well as an array of coordinates, an array of atomic charges, weights, as well as a dictionary of shared attributes along the different conformers. And this is a little bit unique in its implementation. To reduce overhead, we envision that every conformer shares the same connectivity. So you can imagine this being made up of a molecule plus a separate array of how these atoms themselves are positioned. And this allows us to reduce a lot of the overhead on how it might function and be read. Now, this leads us to the final two key classes within Molly for how we serialize these objects. The first is the molecule library, and you can imagine this a lot like a zip file or an HDF5 file. You can either read or write directly from these, and this is just a serialized form of the molecule objects. You have a dictionary where a name of an object points to its binary form that can be read or written to. And it's an unordered dictionary where we use kind of this weak reference approach to retrieve the objects, which allows us to not have to wait for the entire thing to load to be able to operate with it. The conformer library is its analog. You can read and write in the same exact form. It's just this will operate with conformer ensembles instead of molecules themselves. With some of the key classes out of the way, I now want to start touching on some of the utility that exists within Molly, including its ability to parse chemdraws with high stereochemical fidelity. Now, the first one is pretty obvious with its ability to handle point chirality. We essentially read in these kind of z-coordinate hints where if it's a hash, we'll rotate the molecule down, or if it's wedged, we'll rotate it up. But we also have the ability to parse more unique forms of chirality, including planar and axial, which means not only can we recognize when certain full groups should be bent out of the plane, but we can maintain multi-attachment points and even point chirality all within the same molecule just upon initial parse. In addition, we can see different labels associated with different atoms. We can read attachment points, we can read isotopes, and we can, most importantly, read charge and spin so that we can understand when we should and should not add implicit atoms. Now, you might be able to imagine certain instances where this could be useful to maintain both chirality and labels. And so for just a quick example, I have this taxidiene structure. You can imagine just importing molli, configuring the visualization tool, and then just reading the ChemDraw path directly into this file. And we treat it as though it's a dictionary. So if we have a label associated with a molecule, and this doesn't have to be grouped, it just needs to be somewhat near it, we can just add implicit hydrogens in a single line, and this is the output without any type of additional optimization. So you see that the stereochemistry remains true within all of those atoms, but in addition, if you go through the atoms and actually look at the list of atoms, you can see the ones that were labeled 1 and 2. So even though the ChemDraw might be arbitrarily drawn and numbered, we can always carry labels through a transformation. Now, with all of this in mind, since our ChemDraw parser is pretty robust, this allows us to create almost an in silico library assembly line, where if you don't want to work with the Python implementation, you can actually work directly at the command line. If you have some type of core file, as well as substituent files, you can use this to combine the cores and substituents together, write it to some type of library, and even parallelize certain parts, add implicit hydrogens, and optimize with OpenBabel on the fly. And this allows us to create huge combinatorial libraries that we've tested up to at least 96,000 different structures. And with the conformer library format, we can have up to 5 million conformers actually existing within some of these libraries themselves. Another important aspect to molli is its ability to parallelize calculations over an entire molecule or conformer library. You can imagine that molli has its own unique scheduler that will create workers that are able to take something from the source library, prepare the job input, and then run the job directly. We can monitor the job with our own native implementation and then cache the output when it's done. And from the cache, if it was successful, we can analyze the results and write these to a destination library. And we can repeat this for any worker. Now, we can do this locally on a job map function, or we can do this through a cluster. Specifically, we've configured it through the SunGrid engine, but this allows us to operate on both computing clusters and local environments depending on what our needs are. Now, under the molli umbrella, we have a few different tools. We have an interface with RDKit and OpenBabel, which allow us to work with RDKit's implementation of graphs, as well as OpenBabel's optimization features and ability to read in unique file formats. We have the ability to accurately parse ChemDraw files. We have an interface for ORCA for quantum chemical calculations, an interface with CREST for conformer generation, XTB interface for atom property calculation, an NWChem interface for ESP calculation, and a job scheduler for either SunGrid engine clusters or laptops. And really all of this is pointing to the idea that molli is trying to support the application and creation of informatic workflows by unifying everything under one architecture that you could potentially extend outwards, because all of this is just the initial development and could really be extended further depending on what needs there are. Now, to that end, I wanted to offer an example of how molli could be utilized to create an end-to-end workflow. And for this, I'll utilize an example for prediction of rotational barriers for varying K-RAS inhibitors. Now, this figure was recreated in ChemDraw based on an existing JMedChem article that focused on the rotational barrier energy around this axis with varying substituents. And we envisioned that we could take molli directly from a ChemDraw all the way to a predicted rotational barrier energy if we designed the workflow correctly. And so what we did is we took a ChemDraw, parsed it, joined, and added hydrogens, and then we executed an XTB relaxed surface scan of the dihedral angle along this axis to find approximate ground and transition state structures. From there, we could actually use our ORCA interface to both optimize and calculate Hessians before we could actually compute final energy barriers and be able to compare them to both the experimental values. Now, the deviations you see here aren't a function of molli as much as they are a function of the actual functional use, but it illustrates how molli can actually enable unique workflow designs for both cheminformatics as well as traditional investigations. And just so you guys are more aware, I wanted to offer a look into some of the Python backend as to how we kind of go about this type of investigation. So if we were starting from some type of ChemDraw file, we could load this ChemDraw file, find the core structure and its attachment points, find the names of everything in the file, remove the core from these names, and add implicit hydrogens directly to the core. We can specify a library to write everything to, and then we could iterate through all of the remaining names in this ChemDraw file, get their associated attachment points, and then join the core and substrate together with the attachment points of both and give it a new name. From there, we can add implicit hydrogens directly to this structure and use OpenBabel to optimize these with MMFF94. And we can even print the dihedrals for anything we're interested in, and we can write everything to this library above. And if we actually look at the MOLecular LIibrary at the end of all of this, this is the actual structure we get out. And we can see that this functionally worked, allowing us to spot check to make sure everything is functioning the way that we want it to. Now, if we want to take this MOLecular LIibrary and actually run an XDB calculation locally, this is the way this actually looks. If we import molli as well as its associated XDB driver, we can take our source library, which is the one we wrote to previously, and then indicate a destination conformer library for all of the different dihedral conformers along the scan, the number of cores and the total possible cores, and then initiate the XDB driver with these parameters. From there, the job map function allows you to integrate a few different things. You can actually grab the function, the source and destination, any arguments you want to actually give to it, a cache directory to specify, and any additional keyword arguments such as the method or the accuracy and range of degrees, as well as the number of workers that you're looking to utilize depending on what's actually available in your system. Now, once we have the actual output of this, we can take an example ensemble and look for those conformer energies, do any type of mathematics that we need to do, find indices associated with things, and actually structure our plot to create the actual dihedral scan that we're looking at here. And so you can see how one can very quickly assemble a pipeline to be able to do a lot of different transformations very quickly on large libraries at once. I'll leave it there for now, but all of the code itself is available on our GitHub, and you can install this either through PyPy or Conda. We also have a ton of documentation available on our Read the Docs, and this has examples, including the ones that I've shown here today, as well as a variety of other workflow examples that existed within the actual publication itself. This was a huge undertaking, and it was originally the brainchild of Alex Shved in our group, and there have been a lot of people that helped us develop this package to the place that it got to today. So I want to thank you for your time and hope you have a wonderful day.